Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be going through the A-Level Chemistry from AQA Paper 1, June 2020. So this question is about enthalpy changes. Figure 1 shows a Born-Haber cycle that shows the formation of strontium chloride, which is SiCl2. And it shows us some thermodynamic data as follows. It says use the data in table 1 to find the electron affinity of chlorine. So what I would recommend doing is looking at each step and deciding what the enthalpy change is. My general point with this topic is if you're complaining about having to learn enthalpy definitions, then you're doing this entire topic wrong and you don't know what you're doing. Because these definitions are important, and I think this is one of the more reasonable topics, because it helps you shape what these equations are. Each line here, and in a Hess's law cycle, is an enthalpy change. You need to be able to look at these and recognize what enthalpy change it is. And that's why it's important. Don't just memorize what a cycle looks like actually understand what's going on, because they can give you scenarios where the cycle isn't the same as what you're used to, or it could be unfamiliar enthalpy changes. So here we're going from strontium solid and chlorine gas in its standard state to strontium chloride, so that has to be the enthalpy of formation. Next, we're going from strontium solid plus chlorine gas to strontium gas, so we're going from an element in its standard state to a gaseous atom. So that's enthalpy of atomization for strontium. And you can see here as well, we've got Cl2 gas becoming 2Cl gas, so that has to be the enthalpy of atomization of chlorine. However, the enthalpy change of atomization is where you go from when you produce 1 mole of gaseous atoms from a substance in its standard state. We are making 2 moles of gaseous atoms, so here it's actually double that. Next, we're going from strontium gas plus that to strontium plus, so that's the first ionization energy of strontium. And then here we can see it's the second ionization energy. Then, what's going on here? So we've got 2Cl, and it's becoming 2Cl minus, so we've got delta H electron affinity for chlorine. However, like I said before, electron affinity is where you get 1 mole of gaseous 1 minus ions from gaseous atoms. So we've got 2, so it's going to be 2 times that. Then we have 1 mole of a solid ionic compound from its gaseous ion, so that has to be the lattice enthalpy of formation. So it's important to know those definitions, because then it helps you shape this together. Next, what I recommend doing is putting all the numbers in on each arrow, then you know exactly what you're looking for. So the enthalpy of formation is minus 828. That one's dealt with. Then we're looking for the enthalpy of atomization of strontium, which is plus 164. That's done. And then the atomization of chlorine, but there's 2 of them, so it's actually going to be plus 2 lots of 121. That's all good. Then we've got first ionization energy, so that's plus 548. That one's done. Second ionization energy is plus 1060. And then also, we don't know what the enthalpy of electron affinity is, so I'm going to call that 2x. Remember there's 2 of them, and then we've got lattice enthalpy of formation, which is minus 2112. So let's say a question says they want you to find the enthalpy change from here to here. As long as you start here and finish here, it doesn't matter what route you take. So one thing you could do is you could go this way around and then flip the sign, because if you're going from, that would be going from here to here and then the opposite way around. Or you could go this way around like this and follow the same sign, because again, you're starting here and finishing here. Or you could have that arrow there because you're starting and finishing here. So that's why it's important to know your definitions, but also appreciate Hess's law applies here as well in that sense. In this example, we know the enthalpy of formation is this, where you're going from this to this. If you go the other way around, you're starting from this and you're eventually finished with this. So the enthalpy changes are the same. So that means we can say that minus 828 equals 164 plus 2, 121 plus 548 plus 1060 plus 2x minus 2112, as in this thing equals the sum of every enthalpy change this way. So if I tidy the numbers up, that gives us minus 828 equals, and if I just do this now, so 164 plus 2, 121 plus 548 plus 1060. So that gives me minus 98 plus 2x. So that means 2x would equal this minus 828 plus that answer, so minus 828 plus 98, which gives you minus 730. So x would equal half of that, which is minus 365 kilojoules per mole. If you do it this way, you'll never ever get this question wrong, ever. So it says draw a line from each substance to the enthalpy of lattice formation of this substance. So we've got MgCl2, MgO, BaCO2, and then we've got all of these enthalpy changes here. So we need to figure out what factors are affecting them. So if I look between MgCl2 and MgO, same metal ion, the only difference is we have O2 minus versus a Cl2, right? So, and then we also have BaCl2. So if we look at BaCl2, Mg and Mg are smaller than BaCl2. So Mg2 plus, remember, the outermost electrons are closer than, for example, Ba2 plus, which is like, it's got loads and loads and loads of shells. Therefore, that positiveness that's attracting it, the positive metal ion, is lower. So that if you have less strong attraction between this and the Cl, the negative Cls, that means you have weaker ionic bonds, which means that they're going to release less energy when they're made, which means it's going to be less exothermic. So if that's the case, you're going to have BaCl2 being this one here. So that one's off the bat. That's going to be the lowest out of all of them. Now, if I compare Mg and Mg, well, they're both the same metal ion, so that's not really great. But this is going to be 2 lots of Cl- versus an O2-. Now here, this O has an O2-. It's a singular atom with 2- charge. It's going to have a higher charge density, so you can have stronger electrostatic attraction between them, blah, 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 stronger ionic bonds. So it's going to be more exothermic when it forms. So that means this one has to be here. That's got to be that highest, and then therefore that's got to be the next one in between the last. So now it says Table 2 shows the theoretical lattice enthalpy based on a perfect ionic model and an experimental value for the enthalpy of lattice formation of silver chloride. Table 2 shows the theoretical lattice enthalpy based on a perfect ionic model and experimental value for the lattice enthalpy of formation of silver chloride. So what have we got going on here? The theoretical is minus 770, but the experimental is actually more exothermic. So remember that when you're doing lattice enthalpy of formation, you're making bonds. Making bonds is exothermic. So in this case, the experiment seems to show that the lattice enthalpy of formation is more exothermic, which means that the bonding is stronger than what the model predicts. If the bonding is stronger, that must mean that there has to be some covalent character as well as ionic bonding in it as well. Because what happens is the purely ionic model assumes that you've got perfectly spherical positive and negative ions. Whereas when you have partial covalent bonding, what happens is you've got this sort of skewing and polarizing almost of the negative ions electrons being pulled towards this like that. And that strengthens the bond even more, actually. So what's happening here is this must mean, therefore, it's got covalent character, like bonding, or partial covalent bonding, as well as ionic. Okay, so now it says, Table 3 shows some enthalpy of hydration values for these ions of group 1 elements. Here we go. And it says, explain why the enthalpy of hydration becomes less exothermic from Li to K+. So rather than jumping straight to saying something that I've memorized and learning a annoying definition or model answer, I can just have a quick second to compare them. If we're going from Li to K+, the only thing that's changing between these is that the shell numbers are increasing. This outermost electron is further from its shell. That's it. That's the first of all it. So so what's happening is you've got more shells because everything else is identical. What's the pattern here? So the enthalpy of hydration is becoming less exothermic. So if it's less exothermic, now we can try and put an explanation behind it. So clearly this thing has to be playing a role. So the first thing is well, first of all, you've got an increasing shielding. So you've got more because of more shells. So that means that you've got less charge density. That's the only explanation I can think of that would explain this, because again, you've got this teeny ion with like an outermost electron way closer than this, where it's got lots and lots and lots of space around it. So then we need to think, well, this is enthalpy of hydration. It's where you're going from gaseous ions to aqueous ions, and it's less exothermic. Remembering that exothermic is bond making, so you need to think, what kind of bond making is happening here? Well, the bond making is between these gaseous ions, and well, it's dissolving, it's hydrating in water. So it's got to be some sort of bond making between the two. So then you need to think, okay, well, what's happening between these? It's got to be that there's less attraction between the metal ion and the delta negative oxygen on water. And there you go. There's no point jumping into saying something like atomic radius, because these are ions, so atomic radius is already out. Like, just have a second to just do that. It's easier and it means less brain strain. So calcium bromide dissolves in water. Here's some enthalpy data. Use the data in table 4 to calculate the enthalpy of hydration of bromide ions. So I've seen so many people tell me this is how they do it. I do this formula, I do that, this and that. No. Any question where you are given enthalpy data and they want you to find an enthalpy change, you must draw a cycle. There is no excuse. There's no other way around it. I don't care who tells you what to do. There is only one way. All right? If you do it this way, you'll never, ever, ever, ever get an enthalpy question wrong. So rule number 1 is you cannot decide which way the arrows go in the cycle or what's at the bottom or whatever until you decide what you're looking for and what's in the bottom and what we've been given. And doing this makes sure that you're forcibly using those definitions, it stays in your head, rather than memorizing every possible cycle in the universe, because there's no cycle that people often memorize for enthalpy of hydration. The amount of times I've had people say, oh, I don't know how to do this question, I don't know the cycle for this. It's like, you don't need one. So the question says, use the table in data force table to calculate the enthalpy of hydration of bromide ions. Fine. The question's told us the enthalpy of solution of calcium bromide, so we're going from a solid ionic lattice to aqueous ions. Here is the enthalpy of lattice formation of calcium bromide. So the definition says 1 mole of solid ionic lattice made by its gaseous ions. So we're going from gaseous ions to solid ionic lattice. Enthalpy of hydration is where you're going from gaseous ions to aqueous ions. So then you need to look at these and then look at those and think what you could do to make a cycle out of that. So I'm going to pick the enthalpy of solution as my first one. You could do the others, but like this one's a nice one because it involves all the ions in it. So you've got calcium bromide, CaBr2, enthalpy of solution, label the arrows, gives you Ca2 plus aqueous plus 2Br minus aqueous. I've picked that one because that gives us both of them in one. If I chose like, I don't know, enthalpy of hydration and calcium, I just have that on its own. So then, let's treat this as our overall reaction, compare everything else. So we've been told the lattice enthalpy of formation of calcium bromide, which is where you go from gaseous ions to solid. So if we look at this, where's that in our lattice enthalpy of formation? That's the solid that we make from gaseous ions. So if we write gaseous ions down here, then if we're going from gaseous ions to a solid ionic lattice, that's your lattice enthalpy of formation. So then, compare these two. They've told us the enthalpy of hydration of calcium ions, which is where you're going from gaseous ions to aqueous ions. Gaseous ions, aqueous ions. So that arrow has to go up. And if we look, they want the enthalpy of hydration of bromide ions, and also, I mean, like, the only one you should know that goes from gaseous to aqueous is the enthalpy of hydration of bromide, sorry. So that's going to be delta H hydration for the calcium ions. But remember that the enthalpy change here would be 1 mole of gaseous ions are converted into 1 mole of aqueous ions. So in this case, it's going to be 2 times delta H, the hydration of the bromide ions. Then put your numbers in, so you label this. So minus 2176. The enthalpy of hydration they've given us minus 1650. They've given us the enthalpy of solution here, minus 110. And here it's 2x. So this enthalpy change starts from here and finishes here. So that means if you start here and finish here, no matter what route you take, because of Hess's law cycle, the enthalpy change will be the same. So if we go down here and then back up here, we're still starting here and finishing here. So that means this enthalpy change means all of that other stuff here going on. So this means that the enthalpy of solution minus 110 equals, so we're going down this way against its arrow, 2176, flip the sign, and then we're following these, so it's going to be minus 1650 plus 2x, because we don't know what that is. If I tidy that up, we get minus 110 equals 526 plus 2x. So then 2x equals, so minus 110 minus that gives you minus 636. So then x would equal half of that, which is minus 318. And that adds up because it's enthalpy of hydration, you're making bonds, it's exothermic, so that's all good as well. Give the meaning of the term relative atomic mass. It's the average mass of one atom of an element compared to 1/12 of a carbon-12 atom. Next. So sample of chromium contains these isotopes and has a relative atomic mass of 52.1. The sample contains this much of the Cr2 isotope. Calculate the percentage abundance of the other two. So rule number one is, well, first of all, remember that your relative atomic mass is going to be, I'm just going to write RAM because I'm lazy, relative atomic mass equals each one of these masses times their abundance plus all the other ones divided by the total abundance. So rule number one is to list out everything you know first off. So we know that its relative atomic mass is going to equal 52.1. Nice. Now we know the abundance of the 52 Cr is 86.1. So then what I'm going to do is we'll look at the 50 and the 53 Cr. We don't know what those are, but we know that the rest of this 100% has to have been split between these two. So I'm going to call 50, well, let's just say that's x%. So then whatever's left over, once we've taken away the x from that, has to be this. So in that case, the Cr has to be 100% minus the 86.1, because 86.1 of that percent's gone here, minus the x, which is 13.9 minus x%. Cool. So then write down the formula as you do. So 52.1 equals, so we know that this one's 52 times its abundance, so 86.1, plus, well, x, so the mass here, sorry, which is 50 x%, plus the next one, mass 53, and then 13.9 minus x. That's all we know. All divided by the entire total, which should add up to 100, because we're dealing with 100%. So if we now tidy this up, we get 5210 equals, and then it's going to be 52 times 86.1, which is 4477.2, plus 50 times x, which is 50x, plus 53 times 13.9, which is going to be 736.7 minus 53x. So then, if I tidy this up, 5210 equals, well, it's going to be 4477.2 plus 736.7, which is 5213.9. That's that and that tidied up. And then 50 minus 53 is minus 3x. So if I move that across, 3x plus 5210 equals 5213.9. 3x would equal 5213.9 minus 5210, which is 3.9. So then x would equal that divided by 3, which is 1.3%. So at least we know that this one is 1.3%. So the abundance of one of them off the bat, the 51, is going to be 1.3%. So then the other one is the abundance, well, that's just 13.9 minus x. It's going to be 13.9 minus 1.3, which gives you 12.6%. There you go. So it says, state in terms of the number of fundamental particles, one similarity and one difference between 50Cr and 53Cr. So the things that must be different is that they have the same number of protons, or you could say electrons. The difference is the number of neutrons. That's what makes an isotope an isotope. Otherwise, if you change the proton number, you're changing what element it is, and if you're changing the electron number, you've got an ion. The sample of chromium is analyzed in a time-of-flight mass spectrometer. Give 2 reasons why it's necessary to ionize them before they are done. So what happens in a time-of-flight mass spectrometer is what you do is you ionize them, and then you pass them through an electric field. So there's a positive and there's a negative end. Because you've ionized them to make them positive, they'll start bending and moving towards the negative part, and that gives them energy. It accelerates them because there's a force now acting on it, pulling them that way. So it makes them actually start getting faster. Because they're getting faster, they have kinetic energy, and then what you do is you pass them through a field with no electric field. Reason is because they'll all have the same energy now added to them, but the lighter ones will move further than the heavier ones, right? And then what happens is they have an ion detector, and what that does is they'll hit the detector will see a current when the ions hit it, and then that is then converted into an MZ value. So if there's no charge, then they're not going to be accelerated by this, and they also won't be detected by this either. Because if, for example, this uncharged thing, it's not going to go into the positive or the negative part, or accelerate or decelerate. So therefore, that's why we ionize them. So then it's because the ions are accelerated by an electric field. And the other one is that the ions create a current when hitting the detector. And, without that, they couldn't actually be detected. I see this question come up time and time again, and people try to just sort of follow a formula, and then it doesn't work, and they're like, oh my god, I don't know what to do. Use what the question's telling you, look at what the question's asking you, and work with that. Everything you need is here. So the question's asking you to find the time, fine, whatever. So it says, a 53 Cr plus ion travels along a flight tube of length 1.25 meters. It has a constant kinetic energy of 1.102 times 10 to the minus 13 joules. And then they've given you the formula, K equals mv squared over 2 or half mv squared, whatever. And then it says, calculate the time in seconds for this ion to travel down the flight tube to reach this detector, and they've given you the Avogadro constant. So what the link here is it's going to be our velocity, which we're going to then use on the length, and it can find us our time. Ke equals a half mv squared, or mv squared over 2. So then 2ke divided by m will give us v squared. Problem is that we've not been told what m is, although we do know what it is. The thing that's doing the moving is a singular Cr plus ion. That mass number is grams per mole, meaning that every mole of this weighs 53 grams. So 1 mole of Cr3 plus gives you 53 grams. One singular Cr3 plus ion is going to be, well, 1 mole, remember, is this 6.02 times 10 to the 23 of these. So it's going to be that. So 53, divided by Avogadro's constant, or L. Oh, well, that's annoying because I've used L here. So then the mass is going to be 53 divided by 6.02 times 10 to the 23, which gives us 8.8 times 10 to the minus 23 grams. But the problem is this formula wants it in kilograms, so therefore to convert it to kilograms, it'd be 8.86 times 10 to the minus 26, because you're dividing it by 1,000. Now we can work out what v squared is here, because we have k and we have m. I'm actually going to just square root it as well, so I can jump straight to getting that v. This will be 2 times the kinetic energy, which is 1.102 times 10 to the minus 13. And you're going to divide it by its mass, which we just worked out as 8.8 times 10 to the minus 26. Remember that this Ke over m is the mass of whatever's doing the moving, and it's told you in the question there as well. So therefore, this v is going to equal 1.5 times 10 to the 6 meters per second. Now we know that v equals distance over time, which we've now got. So time would equal distance over the speed, or velocity, which is going to be, what's the distance? 1.25 over 1.5 times 10 to the 6, which gives us 7.9 times 10 to the minus 7. There you go. This question's about period 3 elements. Figure 2 shows the second ionization energies of some elements in period 3. So when you're doing these questions about periodicity and it's talking about ionization energies, just double check what you're removing the electrons from, and also look at their electron structure, because that explains everything that's happening. This is a second ionization energy. So this silicon's either higher or lower, and we need to decide. So what I'm going to do is I'm going to compare each of them. So aluminium, silicon, phosphate. So aluminium's period 3, it's in the p block, it's p1. So the outermost electron is going to be what, 3s, 3p1. Silicon is 3p2, so it's going to be 3s2, 3p2. And then it's going to be phosphorus, which is 3s2, 3p3. So first ionization energy is going to be 3s2, 3p0. And then the second one is going to be 3s1 there. This one is going to be the first ionization energy is going to be 3s2, 3p1, and then 3p0. And then the second ionization energy of this one is going to be 3s2, 3p2, and then 3p1. So we need to compare these. So for aluminium, we're removing the electron from the 3s orbital. Remember that that's got less energy than 3p. 3p is further away. It's the next subshell. So it's easier to lose this than it is to lose that. So that means this is harder. Like there's more energy required, so second ionization energy is going to be higher. So compared to silicon, well, we're removing this electron from a p orbital versus an s. So this one's going to be easier. So you're going to have the silicon one's going to be lower than that. Now it says, identify the element in period 3 from sodium to argon that has the highest second ionization energy and give an equation including state symbols to show how this process occurs and the second ionization energy is measured. If you're unable to identify the element, you can use Q in the equation. So the thing with the highest second ionization energy is going to be the thing that has the... So remember what affects this ionization energy is how far away from the nucleus it is. So if you ideally, the nucleus is positive, remember, and the electrons are negative. So you want something that means that it's really, really close to the nucleus that you're peeling them out. So that means it's going to be the smallest thing with the smallest radius, the smallest number of shells. In this case, not ionic radius, it's not atomic radius, it's ionic radius. So in this case, sodium, because we're looking again in period 3, 1, 2, 3, it's going to be sodium, because sodium's outermost electrons are the closest, and we're peeling them away like that. This is the second ionization energy, which is where you have a mole of gaseous 1 plus ions becoming a mole of gaseous 2 plus ions. And there's an electron there. Oh, whoops. I've written the equation down here by accident. It's Na there. Next it says, explain why the atomic radius decreases across period 3 from sodium to chlorine. So in sodium and from sodium to chlorine across this period, you're not getting any extra shells. The only thing that's changing is the number of protons and the number of electrons. So that's it. There's only that only explanation is that. The only thing you can derive from that is there's more protons, but for some reason the radius is dropped because the question's told you that. The only reason for that must be is that the increased protons means an increased nuclear charge, which means you've got increased attraction to the outermost electron. And why? Because they're the same, the same shell numbers. There's no new shells coming in. That's the only explanation that makes sense. So you can memorize that, obviously, but like here, that's fine. So what's the thing with the most electronegativity? It is the thing that's closest to fluorine, which is chlorine. So now it says phosphorus burns in air to form phosphorus 5 oxide. Give an equation for this reaction. So the equation is just one you need to memorize, unfortunately, but it's going to be P plus O2 makes P4O10. You need to recognize that the formula of phosphorus 5 oxide is this. It's not P2O5, it's this. I'm not too sure why, I can't remember, I can't lie, but this is what it is. So then you've got to balance it out. So there's 4 P's there and there's 10 O2s, so there's going to be 5 O2s there. Done. Next it says propanoic acid is a weak acid. The acid dissociation constant is this. What is a weak acid? So it is just that it partially dissociates in water. Write the expression for the propanoic acid, Ka. So Ka equals H plus, and then A minus. So it's just the rest of this acid without the H plus in it, which C double bond OOH, that's the alkoxylic acid. It's going to be C2H5COO minus all over the concentration of the acid, which is C2H5COOH. A student dilutes 25 centimeters cubed of this much propanoic acid by adding water until its total volume is that. Calculate the pH of this diluted solution of propanoic acid. Give your answer to 2 decimal places. So to find the pH of anything in the universe, you need H+. And now you need to think where you're going to get the H+ from. So this is a weak acid. So in order to get H+ from, you're going to have to use Ka. Now your options are Ka roughly equals H+ squared over HA, or it's going to be H+ A minus over HA. Now you need to recognize that A minus is salt in this context because the equilibrium is so far to the left there's barely any of this normally. So A minus equals salt. Is there any salt in this? No. No salt? None this. If you see OH in the formulas, like, KW, then it means there's base in it. No base. So the one we're going to have to use is this. So the problem, though, is that they've now added water and tweaked the concentration up about it. So we need to figure out what's changed Remembering that concentration is the number of moles over the volume, all they're doing is they're diluting this, so they're adding volume to this. So if you, like, for example, double that, then the concentration is going to half. So if we look at what's happened before, we started with 0.05 moles decimeter cubed, and what's that? 25 centimeters cubed gave you this. So we need to find the new concentration, well, they've now made it so it's 100. So 25, what you've done is you've times the volume by 4. So this is times by 4. That must mean you've got a quarter of the concentration. So the concentration of HA must have dropped by 4. So you're going to divide by 4. So that means you will have had 0.125 instead. Mole dm minus 3. Now we have the new concentration of HA. We can find H plus just by rearranging this formula. So Ka times HA equals H plus squared. So if I square root it, I'll get H plus concentration. H plus concentration would equal, well, the square root of, and they've told you in the top part where it was, whatever it is, 1.35 times 10 to the 1.35 times 10 to the minus 5 times the concentration, which is 1.25, which is going to be 1.3 times 10 to the minus 3. pH is going to be negative log to the base 10 of the answer you just got, which is going to be 2.89. So buffer solution questions are the same as any equilibrium question in the universe. You know, where it's like, oh, something's been left here, and then it becomes an equilibrium, and then at equilibrium this much is found. Same thing. So first of all, we'll use a buffer is always a weak acid mixed with its salt, and to find a pH of something, or to do anything with that, we would use Ka equals H plus A minus, which is the salt, over HA. The tricky part, though, is that they've told us we've got the pH, and they've dissolved this much of sodium propanoate, which is the salt, in a solution of propanoic acid. The final volume of this solution is 500 centimeters cubed, and the final concentration of this thing is, the final concentration of the acid is 0.250 moles per decimeter cubed. Final meaning that at this equilibrium point. So it's saying find X in grams. So let's just work out the fundamentals first. We've got Ka, because we're using the same acid, and we can find H plus by just doing 10 to the minus 4.5. The question wants us to find X, which is the amount of salt, which is only linked to here, like from in this formula. So we're going to rearrange Ka, times it by HA, divide it by H plus, and that will give us the A minus concentration. All of this must have come from the salt. So that means the A minus concentration has got to be Ka, which I've already forgotten what it was, 1.35 times 10 to the minus 5, times the HA, so the final concentration of the propanoic acid, because this is all the concentration at equilibrium at the end, not the start concentration. So it's going to be times 0.25. Divided by the H plus we just worked out, which is 10 to the minus 4.5. If I now do that, I get an A minus concentration of 0.106727 moles per decimeter cubed. Now, all of this A minus must have come from the salt that was added, because normally, when you've got a weak acid on its own, there's no A minus in the equilibrium because it's so far to the left. So that means that your concentration of the salt, this whole thing, is also going to equal what we just worked out, the A minus. So we can now work out the moles of the salt and the A minus by looking at the concentration times its volume. So 0.166727 times the volume of this whole thing it's in. Now they've told you that the final buffer volume is 500. We're going to divide that by 1,000. So if I do that, I get the moles of salt to be 0.05336. Now they want the mass of it equals moles times MR, which is going to be 0.053, whatever it was, 6 is blah, 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 times the MR of the sodium propanoate, which you can get from the periodic table. Just to save time, it's 96, and that gives you 5.13 grams. Some reactions of the AlH2O6 3 plus aqueous ion are shown. So what's going on here? So we've got AlH2O6 3 plus, we've added EDTA, fine, we've added... So the Na4 is, remember, just the means of getting the EDTA, and you can't just have EDTA minus on its own. When you dissolve this, it'll split into Na plus and EDTA minus. That's why there's an Na with it. So here we're giving, CO32 minus ions to it, and we're getting a white precipitate. And then also when we add NaOH, you get a white precipitate that reacts to form a colorless solution containing complex ion C. Fine. So then it says, give the formula of the white precipitate B. So these are metal aqua ions, and aluminium's a funky one because it can act as an acid. So if it can act as an acid, anything in the world that acts as an acid means it donates protons, which means it's going to give out H pluses. Anything that can act as a base means it's going to react with the H pluses, by definition. So this is reacting as an acid, and you're mixing it with a carbonate, acid plus a carbonate, carbon dioxide, and water. So if we're going to make a carbon dioxide plus water, we're also making a salt too. So in this case, the salt that must be made, well, all of the C in that carbonate's going into this carbon dioxide. Remember that when you're doing a neutralization reaction, it's H plus OH minus makes H2O. So the other product's H2O, but the H plus must have come from somewhere, which means it must have come from here. The only thing in this that can give out H pluses is this. So if it reacts in that ratio, if it reacts, that means that some of these H2Os are going to become OHs. That's why it does that. So it's not a ligand substitution thing, it's actually an acid-base reaction. So the formula of the precipitate B has to be, if it's making a solid, it's not going to be charged, and it will react in a perfect ratio with these three CO3 2 minus ions, is going to be Al, H2O, some number, and then OH, some number as well, and solid. Now, it's reacting with the carbonate ions, which are 2 minus, and this is 3 plus. So that means it will give away 3 H pluses to this thing. So if it does that, it means you're going to have 3 here and 3 here, because these 3 will have lost an H plus to become OH minuses, and that's what that is. Now the observation is, like I said before, you're making CO2, so you're going to see bubbles or effervescence, whatever you want to say. And then in terms of the equation, we know for sure that the reaction that's going to be going on is that this is reacting with whatever it is we're putting through, so CO3 2 minus. We also know that this is the aqua ion is doing the reacting, so we're going to have Al, H2O, 6, 3 plus that, and I just said as well, we make a salt plus water plus carbon dioxide. So we know we're definitely making H2O liquid plus, let me actually write these state symbols, plus CO2 gas, and we know that we've just said here as well, we're going to make Al, H2O, 3, OH, 3. So you can derive it actually a lot of the time just by thinking about what's going on stepwise rather than trying to memorize these equations. But I need to balance this. So this is CO3 2 minus, that's 3 plus, so it's probably wise if I'd have 2 of these and 3 of them. If you got 3 of these, then we're going to have 3 CO2s because all the carbon's here from here, and then all the aluminiums here must be 2, and then you can just check it all adds up, and what else? Oh, and then we also have 3 H2Os here as well, and there you go, that's it done. So now it says, give the formula of this complex ion C and state one other condition for C to form from this and this, and write an equation. So if we look here, we're making a white precipitate, which is going to be this, but then it forms a colorless solution that contains the complex ion C. So C has to be, so the reason it happens is because you get continued proton donation from these things. So these can continue donating protons until you're losing all of those H2Os. So what you end up getting is you can have Al, OH, 6, 3 minus, or you can have varying numbers of it. So you can have AlH4, or you can have Al, H2O, 2, OH4, minus, or it can go all the way down. Now, why does this happen? It's because, again, those H2Os are losing protons. Something else has to accept protons. What's accepting the protons is the OH here, the base. So we need to make, if we're going to force it to do that, we need to have excess NaOH, because this is an equilibrium thing. So then the reaction equation for this would be, so what is this? It's the overall equation for this whole thing. So we're starting with Al, H2O, 6, 3 plus, in my example, 6 OH minus, aqueous gives you AlOH 6 3 minus aqueous plus 6H2O liquid. That's not a substitution reaction, that is neutralization. So then it says deduce the formula of the complex ion A. So what they've done is they've added EDTA to AlH2O6. So all it is that EDTA just sticks on. So it's going to be Al EDTA, and remember EDTA is 4 minus and Al is 3 plus, it's going to have an overall charge of minus. Explain with the use of an equation where a solution containing this has a pH less than 7. So it's told you in the question that it has a pH less than 7, which means it's got to be acidic. So by definition, you've got to, again, like I said before, every acid in the world puts out an H+. So that means you're going to have Al H2O 6 3 plus can become, well, definitely one of these things has to be an H+ on this side. So then Al, the H plus can only have come from here. So that means you've got H2O, well, Al, H2O, 5. One of these lost an H plus, so what's left is an OH. 2 plus, like that. That's what's going on. And then, why does it do that? Well, it's because, the reason is because Al 3 plus has a small size and therefore high charge density, which means it weakens the OH bond in water, because remember the H plus is coming from here, so the OH bonds in this water have to have broken for that to come off. So weakens the OH bond in water, and that releases H plus ions. By definition, anything in the universe that gives out H pluses is an acid. So for example, HCl, remember that although it's a strong acid, it's still technically reversible, H plus Cl minus. This is an acid because it can give out an H plus. This is a base because it can accept an H plus to become that. That's how acid-base reactions happen. So now it says methanol can be manufactured in this reversible reaction as shown, so whatever here, and it's an exothermic reaction that way. It says here's how the partial pressure changes with time at a constant temperature. Draw a cross on the appropriate axis where the equilibrium the mixture reaches equilibrium. So remember, partial pressure is just concentration, but for gases. All of these are gases, so as the reaction starts up, this is going to drop, this is going to drop, this is going to go up, and eventually it's all going to level out and they're all going to stay constant. So we can see that here, this is the C3OH, which is dotted. You can see as the time goes on, the partial pressure increases and levels out, meaning it's hit equilibrium, and these drop us at the same time, so therefore, around wherever it starts to level out is where our X is. So then it says a 0.230 mole sample of carbon monoxide is mixed with these in a 1:2 ratio and then allowed to reach an equilibrium at this temperature T. At equilibrium, this has this much carbon monoxide, the total pressure is that. Calculate the partial pressure of the hydrogen in this equilibrium mixture. So I always just write a little equation just to make sense of what's going on. So I'm going to do CO2H2 again. So Cl plus 2H2 gives you CH3OH. Now they've told you that this is at the start and then this is at equilibrium. They've told you that we have 0.230 moles of carbon monoxide and it's mixed with a ratio, in a 1:2 mole ratio, with hydrogen. And it's allowed to reach equilibrium, and then at the equilibrium we have 0.120 moles of carbon monoxide. It's a 1:2 ratio, that means we have 0.46 moles of this. At the start of before we've even hit equilibrium, we have nothing here. At equilibrium we will have some amount, right? So we need to look at what's happening. Every single CO will eventually go into this in this reaction. So if this has fallen by, what's that? If that's fallen by 0.110, then this must have gone up, because it's 1:1, by 0.110. So at equilibrium, there's 0.110 moles of this, the product. Every single two of these makes one of those. So if one of these have been made, then two of these must have gone into it to making that. So if that's dropped by 0.110, if that's gone up by 0.110, this must have dropped by 0.220. So that means 0.460 minus 0.22 gives you 0.240 moles. Because the question wants us to find the partial pressure, so we need to find out the total moles of everything, which is just going to be all of these added up, which is 0.470 moles. Now, we want to find the partial pressure of hydrogen. They've told you the total pressure of this whole thing is that. The partial pressure is the total pressure times the mole fraction. So the mole fraction is just whatever the moles of this is over the total moles. So the partial pressure of the hydrogen gas is going to be 1.04 times 10 to the 4 times the fraction of moles that is this. So that's going to be 0.240 over the total, which is 0.47, which gives you 5310 kilopascals. So now it's saying give a Kp expression for this. So remember, it's Kp, we're dealing with pressure, so you can have PCH3OH, you can do PP, whichever one's fine, PH2, and there's two of them in this equation, so it's squared, and then PCO, like so. Sorry, the P goes on the outside, whoops. So there's that. And its units are going to be, well, it's in, so what are they doing? They're doing in, they've given it in kilopascals, so we'll just go with that. So it's kilopascals divided by kilopascals squared kilopascals, which means you're doing kilopascals divided by kilopascals cubed, which is going to be 1 minus 3, which is minus 2, so it's kilopascals to minus 2. So when you're timesing indices, you're adding them. So for example, if I do 2 cubed times 2 to the 9, that's the same as saying 3 plus 9, so 2 to the 12. If I'm doing 2 cubed divided by 2 to the 9, then that's going to be 3 minus that. So it's going to be 2 to the, minus 6. Right? So that's how you do it. So some more carbon monoxide is added to this mixture in 6.2, and then it's allowed to reach equilibrium at temperature T. State the effect, if any, of the partial pressure of methanol and the value of Kp. So if we're looking at adding more carbon monoxide, so the partial pressure of methanol, so remember equilibrium shift to counteract the change. The change you've made is now you've increased this. So to equilibrium, the equilibrium want to decrease this, so it shifts to the right and will make more of this. So if it shifts to the right and makes more of this, then that goes down and this will react to go down as well. So the partial pressure of methanol increases. However, this will go down, this will go up. Sorry, this will go up, but then go down, this will go down, this will level out, this will go up, so it all levels out, so Kp does not change. The only thing that affects Kp, Ka, Kc, Kw, K, anything in the world is temperature, and literally none of the other ones do. So it says state the effect, if any, of the addition of a catalyst on the value of Kp for the equilibrium. There is absolutely no effect. Why? Because it increases the rate of both the forward and reverse reaction by the same amount. So the melting point in CFO is higher than PF3. Explain why the melting points are different, and in your answer you should give the shape of each molecule. Explain why they have that shape, and the shape influences the shape. The shape influences the force that affect the melting point. So for each of them, we need to talk about. So we need to talk about one, the shape, Y, and then also the forces that affect the melting point. So because we're melting things, we're melting the forces between molecules, and these are molecules, so it's going to be intermolecular forces, so how these affect them. So let's start with talking about our shapes. So in XeF4, it has, so Xe has 8 in its outermost shell, but 4 of them are going to fluorine, so it's got 4 bonding pairs, 2 lone pairs. I'm just writing this for short, you need to write the full thing, obviously. Whereas PF3 has 5 in its outer shell, but it's got 3, give it 3 covalent bonds with the F, so that's going to be 3 bonding pairs, 1 lone pair. So the shapes that you will get is that you've got square planar for Xe, and then PF3 is 3 bonding, 1 lone, so that's what, pyramidal. Then it's, so you've dealt with the shape, we need to explain why. Every single time they ask you about why, it's because lone pairs repel, so lone pair, sorry, repels most, then lone pair, bonding pair, then bonding pair. So we've satisfied that part. Now we need to decide how these affect the intermolecular forces. So they've told you that the melting point of this is higher than PF3. So if that's the case, then XeF4 must have stronger intermolecular forces than PF3. Otherwise, what else explains why it's got a higher boiling point? So if that's the case, now we need to compare them side by side. So if we're comparing XeF4 and PF3, well, the things that the intermolecular forces XeF4 has is that it's got van der Waals forces, and it's got permanent dipole. And PF3 also has van der Waals forces and permanent dipole. So we need to now compare them further and see what the differences are. Well, XeF4 has a higher melting point than this. The only other differences between them is that XeF4 physically just has more electrons. XeF4, more electrons, therefore, it has a larger number of van der Waals forces, because van der Waals forces are affected by the strength of the van der Waals forces are affected by how big the molecule is because of the electrons. You can't just say it's bigger, you need to say there's more electrons. But also what affects van der Waals forces is it's saying, explain why the shape also affects it. This is square planar, that's trigonal, that's a pyramidal or trigonal pyramidal. So you can't stack these as easily as those. So as well as that, you can actually, it's got more closely packed together molecules. So there's more surface area for contact. So that means there's even higher van der Waals forces. So that's why. So when you're doing these, step by step it, and remember to compare absolutely everything. Look at them at face value. The only difference between these two is that this has more electrons than that. There's absolutely no other way I can explain either why either of these are behaving the way they are. So again, another question I see a lot of people fumble on because they don't read the question, and for some reason reading comprehension goes out the window, is this. Don't just work out moles blindly, look at it and read what's going on, make sense of what's happening. So they want to determine the percentage by mass of sodium chlorite in a sample of bleach. So what they did is they got bleach. Okay, so what they did is they got 10 centimeters cubed bleach, made it up to 250 centimeters cubed. Then what did they do? They then took 25 centimeters cubed of this bleach dilution. And then obviously people love saying, oh, I titrated this and that. Like, just say what they did, reacted with what. So what they did is they added excess Ki, and that led to I2. Then what they did is they added sodium thiosulfate to this whole thing. So the excess leftover, plus the thiosulfate eventually makes it go colorless, and there's only I- left. Fine. The reason I say that is because you can then figure out how you're going to get back up. So here, it says use all the information given to work out the mass of the NaClO in the original bleach solution. We're going to have to work backwards. Don't work out moles blindly. Think about what's going on. You can't follow formulas. They don't work. Like, you just can't follow the same steps. Every time people get it wrong, and the exam boards know this. If you can't work out, whenever you're working out moles, you need to be able to justify what you're going to do with it straight away. If you can't, then you don't know what you're doing. So if I look here, we got some bleach, reacted it with Ki, but there's too much Ki. If I worked out the moles of Ki and then said, oh, that must be all of the NaClO left, that's going to be higher than what's actually there, because you've got an excess. That's assuming they all react perfectly. So the excess Ki has led to I2 being left behind. If we look at the equations, that's where our I2 is. So this first one eventually leads to I2. Second equation is where they're adding thiosulfate, which is here, which reacts with the I2. All of this I2 must have come from that first reaction. So if I can work out how much I2 is here and here, then I know how much excess stuff is left behind, right? Because all that I2 is the excessy stuff. So I know how much is excess, so I can work out how much actually reacted with the CLOs, because I can subtract that by the total amount of Ki. Then I'll know how much ClO there will be, and then I can work backwards like that. So my first step is to work out the moles of the thiosulfate, S2O32 minus, and the reason is because I'm going to use that to work out the I2. So that's going to be 33.5 over 1,000 times 0.1, which is concentration, because that's his volume. That's his concentration, sorry, volume. And then where is it? That's his concentration, which is going to be 0.00335 moles. Then I know that the moles of the I2 is going to equal a half of that, because it's 2 to 1. And I know that all of this I2 came from this step here. So that's going to be 0.001675. All of the I2 must have come from here, which means that this must also be the same moles of the I2. So the moles of the ClO minus in a 25 centimeter cube pipette, remember, and I also forcibly make myself do that because that's what we're reacting it with, is going to equal 0.001675. So actually, we didn't actually have to do any of the subtracting KOH stuff. We're working out the totals, which is actually a good thing here. So then we've got that. We know that all of this ClO must have come from that 100 centimeter cubed sample. I don't know why I wrote 250. Sorry. So that means in 100 centimeters cubed, there's going to be 4 times as much of that. So it's going to be that times 4, which is 0.00670. So then this is the amount of ClO minus in the original thing. So therefore, the moles of the NaClO has got to equal 0.00670 as well, because that will dissociate into Na plus and ClO minus. So then, if that's the case, then we could work out the mass, because mass equals moles times MR, which is going to be 0.00670 times the MR of the NaClO, which is going to be 74.5, which is 0.499 grams. And then they want the percentage by mass. Well, they told you that the total mass of this thing was what? Okay, so we don't have the original mass. However, they told you the density of the original bleach solution is that. So the mass of the original stuff, well, they told you it was 10 centimeters cubed, and the density is what? 1.20 grams per centimeter cubed. Every single centimeter cubed has this much grams. So if we have 10 centimeters cubed, then that means we're going to have 12 grams. So percentage by mass will be 0.499 over 12, which is, times by 100, which gives you 4.16%. So whoops, I don't know why I wrote 250 there to begin with. I'm going to go back retrospectively and change that to 100. The total uncertainty for this is 0.15. So percentage uncertainty is your uncertainty over your value that you measured. Here, you would think that it would be 2 times this because you would read the volume before and after, but the question's actually already given you the total from the 2 readings. So that's quite cheeky, that. So it's already 0.15 divided by what the burette reading was, which was 33.8, because this was in the other stuff is in the conical flask. This is from the burette. So 33.5 times 100, which gives you roughly 0.45%. Some questions for future reference might say, what could the student do, or something like that, to reduce their percentage uncertainty? So percentage uncertainty, like I said before, is the uncertainty over the value they measured, right? This is going to stay the same if they use the same equipment. So what they could do is they could change the equipment to have a lower uncertainty, or they could just measure a bigger value. If they change this volume to, like, I don't know, 33500, then that's going to make the uncertainty drop. So that's another way of doing it, is you can reduce percentage uncertainties by just measuring bigger things. And that makes sense, because if I measure your height as 180 centimeters cubed, but my uncertainty is plus or minus 10, you could either be 190 or 170, which is terrible. So there's 2 ways around this. One, I could do plus or minus 1, so now your range is what, 181, 179, or for some reason you can just become massive. So if that's 18,000, then now the range of values is what, 17,990, or it could be 18,010. Can you see how that comparatively is a teeny difference compared to this? So this question's about sodium halide. State what's observed when silver nitrate solution is added to sodium fluoride. So whenever you're adding silver nitrate to the halogens, you can either end up with a precipitate or a solution depending on what it is. So these are the general results. So here's AgNO3, here's when you add ammonia, and this is when you add concentrated ammonia. So for F minus, Cl minus, Br minus, and I minus. So if you add silver nitrate, you get a colorless solution. If it's Cl minus, you get a white precipitate. If it's Br minus, you get a cream precipitate. And if it's I minus, you get a yellow precipitate. Then if you add ammonia, well, I mean, there's nothing observations-wise that's changed. I should say dilute ammonia. It dissolves, nothing happens, and in concentrated, that's gone, that dissolves. And then the cream precipitate dissolves, and then nothing happens there. So these are helpful to identify what the mysterious halide could be. When it says state what is observed when the nitrate solution is added to sodium fluoride, or whenever it says state what is observed, it's saying what do you physically see. So if it says something like state what's observed when you add sodium metal to water, it disappears and you get bubbles. It's what you see, not what the reactions happening here is. So in this case, it forms a colorless solution. So now it says state one observation with solid sodium chloride reacts with concentrated sulfuric acid. Give it an equation for the reaction and state the role of the chloride ions in this reaction. So all the halides will react with concentrated sulfuric acid, and the first thing you'll get is NaHSO4 and a hydrogen halide. That's just kind of one of those. It's those group 7 reactions that you've got to learn with sulfuric acids. In this case, it's going to be NaCl plus H2SO4. One of the products is going to be HCl. The other one is what's left behind, which is going to be NaHSO4 plus, and those are that. Those are those there. So it says state the role of the chloride ions in the equation. So if you look at the chloride ions, it's -1, it's -1 still. It's not changing oxidation state, so we can't really talk about anything else in that context. So what we need to do is we need to look at what the Cl- is doing. So the Cl- is stuck to an Na, and then it becomes a Cl- with an H on it. The only difference between the two of these is that it has gained an H+. When anything in the universe gains an H+, I've just realized I've written this in the wrong place. Just pretend that's down here. So there. When anything in the universe gains an H+, it is a base, because it has accepted a proton. Anything in the universe that puts out an H+ is an acid. Anything in the universe that can react with an H+ to make something else is a base. So in this case, that Cl- is a base because it's accepted a proton. And sorry, the equation should be down here. In the observation, well, you get misty white fumes as that HCl is made. So now it says, given an equation for the redox reaction between solid sodium bromide and concentrated sulfuric acid, explain using oxidation states why this is a redox reaction. So all of the halides do the reaction above. So you have Na halide plus H2SO4 will give you NaHSO4 plus H, BrCl, whatever, right? So bromine can take it one step further because it is a stronger reducing agent, so it can actually bring it down to SO2, for example. So in this case, our equation is going to be, well, we're adding NaBr and H2SO4, and one of the products is going to be SO2. The next product is going to be Br2, and the other product is H2O. And then you should kind of just remember that these two are the key things, and what's left over is that. In terms of balancing it, we're going to need 2 NaBrs there, definitely. How many? I can put 2 there and a 2 there. That balances that out. So then it says explain using oxidation states why this is a redox reaction. So if we need to look at what's being oxidized and what's being reduced. So if we look at Br, it's gone from -1 to 0, because the overall charge of this molecule, this thing NaBr, sorry, molecule, is +1 -1. Here it's 0. If we look at sulfuric acid here, that's -8, that's +2, so it's got to be +6. And then if we look at SO2, that's -4 + 4. So its oxidation number, remember oxidation number measures how much oxidizing you've done. So it's been reduced, meaning it's gained electron. So then that Br goes from -1 to 0, oxidized, because you can see that the oxidation number is going more positive. And the S goes from +6 to +4, and it's reduced. Its oxidation number has reduced. It's gained electrons. So now it says state what's observed when you're adding aqueous chlorine to sodium bromide. So this is one of the displacement reactions. So chlorine will displace bromine will displace iodine. So what happens here is you start off with a colorless solution of this. You're adding chlorine, and then it swaps with the bromide to become chloride, and that bromide becomes bromine. So you end up with a yellow/orange solution. The reason we say yellow/orange is because brown would be iodine, so just be careful with that. And then the ionic equation is, well, we're adding Cl2 to NaBr. The Br- ions are what's reacting in this part, the NaBr. That's still Na plus on the other side. So it's got Br-, and it becomes, well, it's swapping with the Br-, so it becomes Cl-, and then the Br becomes Br2. So then to balance this, we're going to need 2 here and a 2 there, and there you go. So methanol is formed when carbon dioxide and hydrogen react. Here you go. And then we've given you the enthalpy of formation and entropy data for these substances. It says use the equation in the data to calculate the Gibbs free energy change of this. So to find Gibbs free energy, we need, so delta G equals delta H minus T delta S. In terms of the things that we have so far, we know that T is 890 Kelvin. We need delta H, we need T delta S. Now, I've said this before in every other paper I've ever done. If you ever get enthalpy data in a table and you need to find an enthalpy change, you must draw a Hess's law cycle, and there's no other way around it. No excuses, no matter what. I don't care what you've been told, I don't care who's taught you what. If you do it like this, you'll never ever get it wrong, right? And the other thing is you cannot decide what your cycle looks like whether the arrows go down or up, until you decide what goes on the bottom. Every single arrow in a Hess's law cycle is an enthalpy change. When you start and finish at the same thing, you have the same enthalpy change. That's why it works. So we're going to use these enthalpy changes to find the enthalpy change of this reaction. So the first thing to do is to write out your overall equation that you're looking for, which is going to be this. 3H2 gas goes to, and we're going to do the forward reaction, CH3OH, gas. And this is the delta H we care about. Because it says formation doesn't mean you can immediately be like, oh, the cycle goes this way. You need to be careful here. Now, the other thing I was going to say is that if you're complaining about having to learn enthalpy definitions and you don't understand why, you don't know what you're doing in this topic and you fumble it horrendously. So once you've decided what your overall reaction is going to be, we need to decide what goes on the bottom. So what you do is you compare what's in your overall equation to what's in the table. They've given us the enthalpy of formation, which is where you get 1 mole of a substance made from its elements and their standard states, blah, 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 blah. So you know the definition, right? So that means that this, compare it to the definition, which side of the equation it would be on. This is going to be the 1 mole of substance, not the elements and their standard states, and this, and this, and this, right? Because they're all enthalpy changes of formation, and that makes sense, because you can't make 1 mole of H2, which for a gas, from its elements in the standard states, because that is the element in the standard states. That's why it's 0. So in that case, what's going down at the bottom is going to be the elements in the standard states, because that's what's common to all of these. Now what you do is you look at this and you compare to the enthalpies that they've given you, because remember, every line is an enthalpy change, and that decides which way the arrow is going. So because these are enthalpies of formation, it goes this way from elements to their standard states to this, because each arrow is an enthalpy change like that. Do not just be like, oh, it's got to go up because it's formation. You'll get it wrong when they give you one that is a mix of them, or if it's different, which happens every time. I see people bringing questions to me all the time on this, and I'm like, stop doing that. The only rule is to do it this way. Next, what you do is you label all of the enthalpy changes. So this is minus 394. This is 3H2. So it's going to be 3 times 0, because it's the enthalpy change when 1 mole of a substance is made, but remember, it's an element in itself, so that's still 0. And then CH3OH, it's 1 mole here, so it's going to be minus 201. So Hess's law says that as long as you start and you finish at the same things, no matter what route you take, the enthalpy change is the same. So this enthalpy change must equal all of these ones going that way. Sorry, just realizing as well, I've just forgotten to add the water there entirely, so there should be an H2O there as well, sorry, and the enthalpy change for that would be minus 242. So then delta H is going to equal, so going against the arrow, 394 plus, sorry, minus 3 lots of 0, minus, and then 201, minus 242. So your delta H should equal, all of that gives you, let's have a look, sorry. So minus 394, minus 201, minus 242, minus 49 kilojoules per mole. Cool, so then what we need to do is we need to work our entropy change. So delta S is S products minus S reactants. It's always, generally speaking, when you're working out a change in something, it's always the thing at the end minus the start. So in Q equals MC delta T, temperature change is temperature at the end minus temperature at the start. If I told you that my weight is now 70 kilograms, last year it was 60, you would do 70 minus 60 in your head. End minus start. That also applies when it comes to things like the weight change as well, if we're talking about it sort of gains and negatives. So if my weight is now 60 this year, and last year it was 70, you should still technically do end minus start, which would give you minus 10, because the change in my weight is minus 10, meaning I've lost 10. So to work out the entropy change, it's just going to be the products. It's going to be what? H2O, which is 189, plus, where are we? Plus 238, minus the reactants, which is going to be CO2, so it's 214, plus, and then there's 3H2, so 3 moles of 3 lots of 131, which gives us minus 180 joules per Kelvin per mole. Now the thing is with delta G is that you've got to keep all the units consistent. So delta G is measured in kilojoules per mole, but we can see here that's in kilojoules per mole, that's per mole, that's happy, that's per mole, that's per Kelvin, so the temperature will fix that part. But here that is in joules, so we need to convert this into kilojoules per Kelvin per mole. So that means if divided by thousands, it's going to be minus 0.180 kilojoules per Kelvin per mole. So then delta G equals delta H minus T delta S. It's going to be our delta H, which is minus 49, minus the temperature, which they told us is 890 Kelvin, and then times delta S, which is minus 0.18. If we do that, we should get 111.2, roughly 111 kilojoules per mole. So here it shows figure 4 showing how the Gibbs free energy change varies with temperature in a different gas phase reaction. The straight line for this graph of the reaction has been extrapolated to 0 Kelvin. Not too shabby. So it says use the values of the intercepting gradient to calculate the enthalpy change in kilojoules per moles and the entropy change for this reaction. So whenever you've got any straight line graph in the universe, it always obeys y equals mx plus c. So that's y, you know, the y-axis. This is your gradient. This is your x-axis, and that's your y-intercept. Whenever you have a straight line, it's always good to compare it to this, then it can helps you read this thing here. So in this case, look at the y and look at the y here. The y-axis in our circumstance, in this case, is delta G, and our x-axis is the temperature, right? So now we've got delta G equals the gradient times the temperature plus C, right? Now, what you should do is relate it to delta G equals delta H minus T delta S and see what the matching parts are. So delta G matches here. We can see there's a T here, but it's got this part stuck on it. So if I compare this MT to minus T delta S, this positive MT with that, it must mean that M has to be this, the delta, negative delta S here, because it's times onto the T. So that means that M is going to be minus T delta S. Sorry, no, M is going to be minus delta S, sorry. And then if we look at the other part of the equation, we've got delta H here, and that's only, you know, again, that's not got like a Y or an X, you know, or Y and a Y and or X. So that means that this thing has to be what's left over, which is the plus C. So the plus C is going to be delta H. So now if we put this in its straight line equation form, delta G equals minus delta ST plus delta H, which is Y equals MX plus C. The question wants us to find the enthalpy change and the entropy change. So the enthalpy changes are a y-intercept. The y-intercept is where you set x to be 0. When x is 0, that becomes 0, and all it is y equals c. So if we set t to be 0, then delta g is going to be our y-intercept. So if you look at this axis here, where t is 0, that's your y-intercept there. So delta g is going to be your y-intercept, which is, and you can see that's about what, 145 kilojoules per mole. Now, if you look here, we can see that our gradient, remember from what we just figured out, is going to be minus delta S. So it's actually the opposite of what delta S should be sign-wise. So to work out the gradient, it's always your second coordinate, y, versus your first y coordinate, minus your first one, sorry, over x2 minus x1. A common mistake I see is that people will pick this, and like this, for example, and then what they'll do is that they will say that's the y2 and that's the y1. That's incorrect, because what you're doing is you're taking away this higher point from the first point, and that will give you a positive gradient. y2 is always that way, right? So as in you read a graph from left to right. So the more to that side you're going, this way, the higher that number gets. So your y2 is actually the second point here, right? So if I choose here, for example, that's my y2, there's my y1. That's your x2 and y2. That is your x1 and your y1. It's essential that you get it the right way around, otherwise you'll end up assuming the gradient is positive instead, and you'll get the wrong answer. So if we do that, then y2 minus y1, well, y2 is 0 in this case, minus the original y value, which is 145, over our second x coordinate, which is roughly 860 minus 0. If we do that, we should get minus 145 over 860, which is roughly, what's that, minus 0.1686. And they want it in joules per Kelvin per mole. Remember that this is in kilojoules per mole. Kilojoules per Kelvin per mole. So to convert it to joules, you times it by 1,000, which is going to be minus 168.6. Or in this case, I should probably give the same number of significant figures as minus 160. So there you go. So always remember that the second coordinate is always the one that's to the right of the first. Even if it's on the previous part here, like in the negatives, it's the one to the right is your second coordinate. Otherwise, you'll mistakenly say the gradient is positive. And the fact that the number works out to be negative is supportive, because a negative gradient goes down. Now it says, state what figure 4 shows about the feasibility of the reaction. So in Gibbs free energy, feasibility is when G is less than or equal to 0, right? That's all it is. So whenever it's less than or equal to 0, it should be feasible. So look, if we look at this figure, we're looking for where delta G is less than 0. So delta G is on this axis, right? Now, it's feasible when delta G is 0. So it's 200 here, it's 150 here, it's 100 here, it's 50 here, so it's 0 there. So then, if it's here or below the graph, then it's feasible. So what you should do is then trace across and find out where that point is. So here, if you see anything that's beyond the 800 and what's that, 40-ish mark, your delta G is less than 0. Anything before it, it is higher than that. So that means that above, as in to the right of, 840 Kelvin, delta G is less than or equal to 0. Well, I should say at or above, sorry. Therefore, it's feasible. And then below, delta G is greater than 0, so it's not feasible. While we're here as well, let's just talk a bit about feasibility real quick. Feasibility means that when you start a reaction, as long as you have the activation energy for it, it will continue without you having to put additional energy into it to completion. So for example, if you boil water, right, and turn it into gas at 100 degrees Celsius, this is feasible, meaning as long as you hold it at 100 degrees, it will do its thing. Because a reaction depends on two things. One, collision in right orientation, but remember, loads of particles collide all the time and they don't always react, so it's also the activation energy. Any reaction in the universe should like, you know, do it and continue and finish, so long as you have those two things. But that's when a reaction is feasible. When a reaction is feasible, it means you've given them enough activation energy so they will collide in the right orientation and react. If it's not feasible, and that means it'll do it as long as that temperature is held. So for example, 100, it will just, you know, it will continue boiling as long as I keep it at 100, because that'll mean they have enough activation energy. When something is not feasible, it doesn't mean the reaction is impossible. It might mean, for example, let's say I have some redo what I just said about the feasible right after the last bit. If a reaction's not feasible, it doesn't mean it's impossible. It just means it might not follow this. So what I mean by that is, imagine we have some other mysterious compound like water 2, right? You know, some aliens come from outer space and like, we bring water 2 with us, we come in peace, and they give us water 2. We try boiling it, and at 100 it starts boiling, but then as you're boiling it, you need to provide more and more heat. So it actually starts boiling at maybe like 100, but then after it's done a bit of boiling, you need to put it up to 120, then 140, then 160. You see how the activation energy just isn't staying like consistent. You can't just keep it at 100 and it'll do its thing. That's where it's not feasible. You're having to put more energy into it as time goes on, or you might have to just continually keep putting more and more in to keep it going. So that's what non-feasible means. The other thing to appreciate is that a lot of reactions are feasible, but may not happen, and there's multiple reasons why. So for example, if you put magnesium in water, it does dissolve into magnesium hydroxide, but it is very, very, very slow. So it almost looks like it's not doing anything at all. So delta G, although it can be feasible, sometimes a reaction might not happen for multiple reasons. One, the activation energy might be like ridiculously high, or it could be that, you know, it's just happening so slow you can't tell it's happening, but it's still feasible. If you left it for years and years and years, it might finish. So that's what all the feasibility stuff is. And the same applies to feasibility when you're looking at electrodes as well, electrode potentials. So if EMF is more than 0, then that reaction, that redox system, is feasible. If it's less, then it is not. So this question is about a glucose-oxygen fuel cell. When the cell operates, glucose molecules react with water at the negative electrode and they form CO2 and hydrogen ions. Oxygen reacts with the hydrogen ions to form water at the positive electrode. So use the question and what it's telling you and work with that. So deduce the half equation for the reaction at the negative electrode. So you know off the bat, it's told you in the question, definitely told you, like, that's C6H12O6 plus some amount of H2O gives you, and they've told you what, to make CO2 and hydrogen ions. CO2 and then some amount of hydrogen ions, right? So what we need to now do is we've got to just look at everything here and see, like, you know, what oxidation states have changed and what electrons and things we need. So with all of these things, you should start by balancing the elements. Balance elements except H and O. Technically speaking, you should always balance electrons first based on oxidation numbers. And then what you do is you balance with water. So you add H2Os in, and then you add H pluses to, you know, to balance the H2Os out. If you do that, that will always get you your half equations fine. In this circumstance, we've got parts and bits and bobs. So you can see there's H's on both sides, so we need to have a look at what's going on between those. So in this case, Oxidation state of oxygen here is -2, so that's 6 of them, so it's -12, that's +12. So the oxidation state, that has to be 0. Whereas here, we've got what? That's +2, that's -2, and then the oxidation state here is +4, and then, what's that, -4? And then here is +1. So we can see that this carbon has gone to +4, right? So that means its oxidation state's gone up by 4, so it's lost 4 electrons. So C's lost 4 electrons. So there's 6 carbons here. So we've got to have, for each carbon, there's got to be +4 electrons here. Now, we figured out the oxidation part, the electrons parts. Let's balance every element except hydrogen. So 6 carbons here. There's got to be 6 here. So that means we're actually losing 4 times the 6. So it's going to be 24 electrons here, right? So we've done that part. So now what we do is we balance the oxygens and the H2O. So we've got 6 oxygens here, right? So we're adding some amount of H2Os to give you 6 CO2s and stuff. So in this case, I'm going to add, well, there's 12 here, and there's 6 CO2s here, and some amount of H pluses here. So we'll put a 6 there, so it's 12 plus 12, because then that's 24 electrons. That would give us 24 protons, because all these H2Os and those H pluses are all going to turn into this eventually, and we need to balance the charges, so it's a double whammy there. And then here we go. Actually, that's the whole thing done. So that's what you could do. In this circumstance, it doesn't follow perfectly, because obviously we've got water already here and H pluses on this side as well. But this applies to like every other metal one in the universe. So then it says, deduce the half equation for the reaction at the positive electrode. So at the positive electrode, it's told you that O2 gas is reacting with hydrogen ions, and it's forming water, the positive electrode. So again, half equation means we're going to have to add electrons. We need to balance the electrons based on oxidation states. So the oxidation state of oxygen here is 0, that's +1, but then here you can see it's +1, and there's 2 of them, so there's 2 lots of +1, and then there is a -2. So the oxygen has gone from 0 to -2, so it's gained 2 electrons, right? Now there's 2 oxygens here, there's 1 here, so we need to put a 2 there to balance that out. So since one of them's gained 2 electrons, there's 2 of them now, so it's going to gain 4 electrons. So we've balanced based on the electrons. We balanced every element except H and O because there's only H and O in this. We balanced the H2O with the waters because there's 2 H2Os here, there's 2 O's here, so that balances out. And then we just add H's to balance out the H2Os. So there's 4 H's on this side, so there's got to be 4 there. And there you go. So then it says, give the equation for the overall reaction that happens in the glucose-oxygen fuel cell. So what you need to do is balance the electrons because it's on this side and this side here. So times that by 6 and you stick them together and you should get C6H12O6 plus 6O2 gives you 6CO2 plus 6H2O. Next it says the negative electrode is made of carbon and the positive electrode is made of platinum. Give the conventional representation for the glucose-oxygen fuel cell. Fine. So the rules for conventional representation is that the reduced forms, this is for each half cell. So the reduced form goes on the outer edge, or the outer side, and the oxidized form goes on the inner. You separate different phases with a straight line like this, or if it's the same phase, you put a comma, right? The other rule as well, though, if you're using electrons for the same phase, is you should also add a line to the outer part for the electrode as well. And as well as that, the other rule is that the more negative one is on the left. So the more negative one's on the left, which is your oxidized, and the positive's on the right. And the E cell is going to be, people like to learn right minus left, reduced minus oxidized. So then if we look here, we need to figure out what's being oxidized, what's being reduced. So in a conventional representation, the other thing you have to include is absolutely everything, elements-wise and stuff, right? So what I mean by that, or species-wise, sorry, is what I mean is that we know that this is getting oxidized, and these two, are getting, the oxygen's getting reduced. But because there's H2O appearing in this, we're going to have to factor in the H pluses as well on either side. Otherwise, it wouldn't make sense. The whole point of a conventional representation is you're supposed to be able to read it from left to right and know what the reaction's going on, and also how to work out the MF. So in this case, if I were to have just written the H2O on the other side, there's no explanation as to where the H2O is coming from and the H pluses and stuff. So we have to put everything in. In this case, we know that on the left-hand side is going to be the oxidation of the C6H12O6. C6H12O6 aqueous. Now I know that's going to become CO2 as one of its products, gas. And I know that the electrode that they've been using is made of graphite or carbon. So we've got a carbon electrode there. Just move this to the side a little bit. On the other side of this cell, we know that the oxygen has been reduced into water. So we know that it's going to be O2, and there's going to be H2O. So that's gas, sorry. That's liquid. And we know it's a platinum electrode. However, there's no H's in this, and that would not make any sense as to how this is happening. So what we need to do is we've actually got to add an H plus here as well to factor that in. But then where's that coming from in this side? So you've got to add an H plus here as well. Otherwise, it wouldn't make sense. So that's why it's this. The other thing as well is that these are in the same phase. I know it says aqueous and liquid. Phase is just like solid, liquid, or gas kind of thing. And so these two are going to be dissolved. And well, that's going to be dissolved, and this is a liquid. So it says, state what must be done to maintain the EMF of this fuel cell while in use. Well, you need to just constantly add glucose and oxygen. Otherwise, it wouldn't work. And there you go. Thank you very much. I hope that helped. Please like, share, and subscribe. You know the drill.